Have you ever stopped to think about why things have weight? Why objects don't just float off into space, or why you don't fall through the floor? At first glance, it seems obvious. You step on the ground, gravity holds you, and everything stays put. But if you look closer, you realize there's a much deeper question. Why does matter itself have mass at all? Why do the tiny particles that make up the world, electrons, protons, neutrons, have the weight they do? This question baffled physicists for decades. The equations that describe the universe worked perfectly well mathematically if all particles had no mass, moving freely at the speed of light. But that clearly isn't what we observe. Electrons have mass, protons have mass, and without it, atoms wouldn't form. Without atoms, there would be no chemistry, no planets, no life. Everything we take for granted depends on mass. And yet, the math said particles shouldn't have any. To understand the puzzle, imagine a skating rink. A perfectly smooth, frictionless rink. If you push a skater, they glide forever without slowing down. That's what massless particles would do. They would never stop, never slow, and would always move at the speed of light. But electrons don't do that. They move, but they have a kind of resistance to acceleration. They have mass. So, what is the invisible mechanism that makes them heavy? Or in other words, gives them mass? Scientists began to suspect there must be something filling all of space, a kind of invisible substance that interacts with particles, slowing them down, giving them weight. But unlike the air or water we are familiar with, this something is strange. It doesn't clump together. It isn't made of ordinary matter, and you can't see it, touch it, or measure it with everyday tools. It exists everywhere, at all times, permeating the entire universe, even the empty space between galaxies. Physicists called this the Higgs field, an invisible field that gives mass to particles when they interact with it. But the Higgs field alone is not enough to explain the phenomenon. Like any field in physics, it must have a particle associated with it, a ripple, a quanta that can be measured and detected. That particle became the focus of one of the greatest quests in modern physics, the Higgs boson. This particle is the key to understanding why the universe has structure, why particles have mass, and ultimately, why anything exists in the way it does. The prediction of the Higgs boson wasn't a wild guess. It emerged naturally from the mathematics of the Standard Model of particle physics. In the 1960s, Peter Higgs and several other physicists realized that without such a field and its particle, the equations describing fundamental forces would not produce the universe we see. Yet, predicting it was one thing, finding it was another. For decades, physicists could only theorize about it. Detecting the Higgs boson would require experiments on a scale never attempted before, something capable of probing the tiniest distances and the highest energies, essentially recreating conditions similar to the birth of the universe. Understanding this is crucial because the Higgs is not just another particle. It is the particle that explains why particles have mass at all, why matter can form, and why our universe has the structure necessary for life. Without it, electrons would move unchecked, atoms wouldn't form, and nothing as we know it could exist. The entire universe depends on this invisible, almost mystical field and the tiny ripple within it, the Higgs boson. Now that we know why mass is such a puzzle, let's talk about the particle that solved it, the Higgs boson. Imagine trying to find a single grain of sand in the Sahara Desert, but the grain only appears for a fraction of a second every time you look. That gives you a sense of the challenge physicists faced. The Higgs boson is not something you can see with your eyes, and it doesn't interact with ordinary matter in ways we can easily measure. Its existence is subtle, fleeting, and incredibly rare. That's why it remained hidden for nearly 50 years after it was predicted. Physicists predicted the Higgs boson in the 1960s. Peter Higgs and other theorists realized that if a certain type of field existed throughout the universe, particles could push through it in different ways, acquiring mass along the way. But the Higgs field is invisible. You can't see it or touch it. You can only detect it indirectly, by finding the particle associated with it, the Higgs boson itself. Detecting the Higgs boson would be like detecting the ripples in a pond caused by a pebble dropped into the water, but doing so in the middle of a storm. To find it, scientists built the Large Hadron Collider, the most powerful machine ever constructed. It's essentially a 17-mile ring buried underground, designed to smash protons together at incredible speeds. When protons collide at these energies, the Higgs boson can appear for a brief moment before decaying into other particles. Detecting it requires observing those decay patterns and reconstructing the event, like figuring out what happened in a car crash by studying the debris. This is why the discovery of the Higgs in 2012 was such a monumental achievement. It wasn't just about proving the particle exists. It was about confirming that our understanding of the universe's fundamental structure was correct. Why does this particle matter so much? Because it answers one of the deepest questions in physics, why anything has mass at all. Electrons, protons, and other fundamental particles are not heavy on their own. They acquire mass by interacting with the Higgs field. Without this interaction, there would be no stable atoms, no chemistry, no planets, no life. You wouldn't exist to even ask the question. The Higgs boson, tiny and fleeting though it may be, is directly responsible for the universe taking the form we recognize. Yet even with this discovery, the Higgs boson is still mysterious. We know it exists, and we know roughly how it behaves, but questions remain. Why does the Higgs field have the exact strength it does? Could there be other fields or particles we haven't yet discovered that interact with it? Could the Higgs be a doorway to phenomena beyond the standard model, like dark matter or extra dimensions? These are questions physicists are still grappling with today. The discovery of the Higgs boson answered one crucial question, but it also opened 100 more. The story of the Higgs boson teaches us something profound about science itself. It shows that some truths about the universe are invisible, subtle, and counterintuitive. You can't stumble upon them. They require decades of careful thought, precise experiments, and a willingness to explore the invisible. And yet, once revealed, these truths illuminate the universe in ways that change how we understand reality at its most fundamental level. Even after the Higgs boson was discovered, it remains deeply mysterious. Why is it so hard to understand, and why does it challenge the way we intuitively think about the universe? The problem is partly that the Higgs exists in a realm utterly different from our everyday experience. We live in a world of objects, gravity, and friction, things we can see, touch, and feel. But the Higgs field is invisible. It doesn't glow, it doesn't push or pull in any way we can detect with our senses. Its effects are subtle and only become apparent when you observe interactions at the tiniest scales. Human brains are wired to understand tangible cause and effect. We evolved to catch a ball, not to reason about invisible fields that fill the entire cosmos. That makes the Higgs almost impossible to visualize. The Higgs boson also operates in the quantum world, a domain that defies everyday intuition. In quantum mechanics, particles don't have definite locations or speeds in the way we expect. Instead, they exist in clouds of probability, and events happen in ways that seem random until measured. The Higgs field gives particles mass, but it doesn't push or pull in the classical sense. Its interaction is subtle and abstract, something you can only describe mathematically. Explaining it with words or pictures is like trying to explain color to someone who has never seen light. You can use analogies, but they are always imperfect. Physicists often use the party analogy. Imagine a room full of people standing still and chatting. When a famous celebrity enters, people cluster around, making it harder for them to move. The celebrity slows down because of all the interactions, similar to how particles acquire mass when moving through the Higgs field. It's helpful, but the analogy falls short in capturing the elegance and strangeness of quantum fields. The Higgs doesn't choose to interact, and the universe isn't consciously guiding it. It's simply the natural result of a field that exists everywhere. Another reason humans struggle with this concept is the scale. The Higgs boson is unimaginably tiny, and its effects are only apparent under extreme conditions, like those recreated in the Large Hadron Collider. We are used to seeing cause and effect in everyday life. Push a rock, it rolls. But the Higgs field is universal, continuous, and subtle. Its presence is inferred from tiny, fleeting effects in particle collisions, events that happen billions of times faster than a blink of an eye. Our brains are not built to intuit phenomena on such scales. Even after decades of experiments, there are still open questions. Why does the Higgs field have exactly the value it does? What determines its strength? Could there be other fields, other particles, waiting to be discovered that interact with it? The Higgs answers one fundamental question about why mass exists, but it also exposes the limits of our understanding, showing us how much of the universe remains hidden behind layers of subtle, invisible structures. Ultimately, the Higgs boson challenges us to think differently. It shows that the universe is stranger than what we can see, feel, or intuit. Mass, something so ordinary in our daily lives, is not an inherent property of matter. It emerges from interaction with an invisible field that permeates everything. Understanding it requires abstract thinking, mathematics, and experiments on scales far beyond human perception. This is the nature of modern physics. The universe is far more subtle and elegant than our senses suggest. To truly grasp the Higgs boson, it helps to step into thought experiments and analogies, because our everyday senses cannot perceive it. Physicists often rely on metaphors to explain the invisible mechanics of the universe, and the Higgs field is a perfect example. One of the most famous analogies is the party analogy. Imagine a crowded room full of people, talking and moving about. When a celebrity enters, people naturally cluster around, slowing the celebrity's progress. The more people gather, the harder it becomes for the celebrity to move across the room. This is similar to how particles acquire mass by interacting with the Higgs field. The field is everywhere, and particles drag through it, gaining resistance that we experience as mass. Another analogy is honey. Imagine particles moving through a jar of honey. The honey resists their motion, effectively slowing them down. The more a particle interacts with the honey, the heavier it behaves. This is not a perfect comparison. Particles don't literally stick to a substance, but it conveys the idea that mass emerges from interaction, not as an intrinsic property. Mass is relational, not absolute. Without the Higgs field, particles would be massless, electrons would zip around at the speed of light, atoms would never form, and the universe as we know it would not exist. Thought experiments also help us explore why this discovery is profound. Consider a universe without the Higgs field. Electrons and quarks would have no mass. They would not slow down or bind together. Protons, neutrons, and atoms could not form. Matter as we understand it would be impossible. There would be no planets, no chemistry, no stars, no life, and no observers to even ask the question. This extreme scenario highlights how the Higgs is not just another particle in a long list. It is the foundation of physical reality. The Higgs also teaches us about the subtlety of science. Unlike a planet or a rock, it cannot be directly observed in everyday life. Its existence is revealed through tiny signals in particle collisions, patterns that emerge from trillions of interactions at unimaginably high energies. Detecting it required decades of theoretical work, massive engineering projects like the Large Hadron Collider, and sophisticated data analysis. The Higgs boson shows that fundamental truths about the universe often exist far beyond our intuition, waiting for humans to invent ways to see them. Philosophically, this changes how we perceive reality. We are so accustomed to thinking of mass and matter as inherent, unchanging properties, yet the Higgs shows that mass is a product of interaction with an invisible, pervasive field. Even the most familiar aspects of reality, weight, solidity, resistance to motion, are emergent phenomena. They are consequences of processes we cannot see, yet which make our world possible. In a way, it reminds us that what we perceive directly is only a fraction of what exists. The universe is a web of invisible interactions, subtle forces, and emergent properties that give rise to everything we experience. By using analogies and thought experiments, we can begin to approach the unseeable. The Higgs boson is not a particle you encounter in daily life, but it is intimately connected to everything that exists. Understanding it invites us to think about the universe in a new way, as a place where reality is not self-evident, where even the most ordinary things are the product of profound, invisible structures, and where discovering a single particle can change how we see the cosmos forever. Even after discovering the Higgs boson, science has only answered part of the story. We know that the Higgs field exists, filling all of space like an invisible ocean. We know that particles acquire mass by interacting with it, and that without it, the universe as we know it would not exist. Experiments at the Large Hadron Collider have confirmed the Higgs boson's presence and measured its properties with remarkable precision. This discovery completed the Standard Model, the framework that describes all known fundamental particles and forces, except gravity. The Higgs is not just another piece of the puzzle. It is the keystone that allows matter to exist at all. Without it, there would be no atoms, no chemistry, no stars, and no observers to even contemplate these questions. Yet, in the same breath, the Higgs reveals how much we still do not understand. Why does the Higgs field have the exact strength it does? Why does it allow particles to acquire the masses we observe rather than slightly different ones? Even small changes in the field's strength could make life impossible. Physicists call this fine-tuning, and it remains one of the great mysteries. Could there be deeper principles or other fields we haven't discovered that explain why the Higgs exists exactly as it does? Might the Higgs boson be connected to phenomena beyond the Standard Model, such as dark matter, dark energy, or hidden dimensions? These are questions at the frontier of modern physics, where experimentation becomes harder and the mathematics more abstract. Humans struggle to fully grasp the Higgs boson because it exists outside the realm of direct experience. Our senses evolved to understand objects, movement, and cause and effect in the macroscopic world. The Higgs lives in the quantum realm, where probability, uncertainty, and fields dominate. It reminds us that the universe is stranger than we imagine. What feels solid, heavy, and inevitable, our own mass, the solidity of matter, is actually a delicate outcome of invisible, subtle interactions at the smallest scales. Mass is not inherent, it is relational. It emerges from interaction with a field that permeates the cosmos. This overturns our intuitive understanding of reality. The Higgs also offers a profound philosophical insight grounded in science. We often take the physical world for granted, assuming that weight, matter, and structure are simple and obvious. Yet the Higgs shows that even the most fundamental aspects of reality are emergent phenomena, arising from underlying processes we cannot see with our eyes or touch with our hands. Reality is not self-evident. It is a tapestry woven from invisible threads. Discovering the Higgs boson is not just a triumph of experimental physics. It is a revelation that challenges our assumptions about what is real and how the universe is constructed. In this light, the Higgs boson changes how we see the universe and ourselves. It reminds us that our everyday experience is just the surface of a far stranger, more intricate reality. Every time you feel your weight, hold an object, or step on the ground, you are experiencing the subtle effects of an invisible field that stretches across the cosmos. This tiny, elusive particle, discovered after decades of work and monumental experiments, is the reason the universe has structure at all. Understanding it invites us to see reality as more subtle, more relational, and far more fascinating than we could ever perceive with our senses alone. Science doesn't just describe the universe, it illuminates its hidden layers, revealing that the world is far richer, stranger, and more interconnected than we can imagine. The discovery of the Higgs boson is more than just a milestone in particle physics. It forces us to rethink what we consider real. For centuries, humans have assumed that mass, weight, and matter are intrinsic, obvious properties of the world. You pick up a cup, it has weight. You step on the floor, you don't fall through. It seems simple, tangible, self-evident. Yet the Higgs boson reveals that what we experience as the solidity and substance of reality is actually the result of invisible processes at a level we cannot see. Mass is not a built-in feature of matter. It emerges from interaction with an invisible field that pervades the entire universe. This means that the ordinary, familiar reality we live in is underpinned by subtle, almost magical interactions at the quantum level. Every object, every particle, every atom owes its very existence to this field. The electrons in your body, the protons in your cells, even the helium in the stars are not heavy on their own. They acquire mass through the Higgs field. Without this interaction, they would zip through space at the speed of light, never forming atoms, molecules, or structures capable of supporting life. In other words, the Higgs boson is not just another particle on a chart. It is the particle that allows reality itself to cohere. The universe would be unrecognizable, and we would not exist to question it. This is both humbling and exhilarating. It tells us that what we consider ordinary, the very weight of matter, is a consequence of something profoundly subtle and unseen. The Higgs boson also teaches us about the limits of human intuition. Our senses evolved to handle everyday phenomena, catching a ball, walking across a room, seeing objects fall. Quantum fields, probability clouds, and emergent properties do not fit neatly into these instincts. The Higgs is a reminder that the universe operates on rules far stranger than our immediate perception allows. Science becomes our tool for bridging the gap between intuition and reality, showing us structures, interactions, and phenomena that are invisible to the naked eye, yet fundamental to existence. It forces a shift from thinking of matter as a static thing to understanding it as a dynamic consequence of fields, interactions, and emergent effects. Philosophically, this opens up a new way of seeing the world. If the mass of every object depends on invisible fields, then reality is relational. Nothing exists in isolation. Everything emerges from interaction. Even the most ordinary elements of life, weight, solidity, resistance, are the result of unseen forces. The Higgs boson reminds us that our perception captures only a small fraction of the universe's complexity. The universe is deeper, richer, and stranger than the surface suggests, and our scientific discoveries are revealing these hidden layers one by one. In this sense, the Higgs boson changes more than physics. It changes perspective. It encourages humility, curiosity, and wonder. It shows that even the seemingly obvious is underwritten by invisible, elegant, and interconnected processes. It invites us to see the universe as an intricate tapestry where the ordinary emerges from the extraordinary, where matter itself is the product of subtle cosmic interactions. Understanding the Higgs boson is not just about understanding a particle. It is about seeing the universe in a profoundly new way, realizing that what we take for granted is held together by processes so subtle that they can only be detected with decades of thought, ingenuity, and experiment. The Higgs boson quietly holds reality together, reminding us that science allows us to glimpse the hidden rules of the cosmos and to appreciate the astonishing complexity of existence itself.